Today's video is about FMEDAs, also known as failure mode effect and diagnostic analysis. One of the most popular safety analysis techniques that's used in the safety critical industry, be it ISO 26262 or IC 61508, is an FMEDA. An FMEDA is a very powerful way to quantify what is the risk that is existing once all the diagnostics in a product have been built. Now, talking about FMEDAs and how an FMEDA is different from an FMEA, there are some differences which are explained in a separate video. For this video, we will just look at what an FMEDA is and what is the process, and we can do an example of an FMEDA. So essentially, FMEDA is a systematic analysis technique which one can use to understand how good is a system when it comes to handling failures. How good can it react to it? How good can it detect it? And how good can it remain in a safe state once it detects it? It is a quantitative analysis technique as opposed to many other safety analysis technique like the HAZOP or maybe even a qualitative FMEA. There's several names that people give to it as well. The past has been known as DFMEA. The most common wording that is used today is the FMEDA, or failure mode effect and diagnostic analysis. So the basic idea is it involves identifying all the components of a product, identifying failure rates and their distribution based on, let's say, environmental conditions, stress, etc. Identifying safety mechanisms that can prevent certain failure modes, identifying how effective these mechanisms are to detect failure modes. And then what can also be done is identifying the efficacy of latent faults. This is something that cannot be done in an FMEA. And finally, overall, it is to predict the useful life of the product. And what this term useful life of the product we're going to define also. Here's a simple process of how to perform an FMEDA. It is inspired from an FMEA process, but it's slightly modified. So the first step, planning preparation. What is the timing? What are the tools? Who are the people? Step 2, once you have the tools and the process defined, you need to identify what is it that you're performing an FMEDA for. So it could be a power supply, it could be a circuit diagram, it could be a microprocessor, it could be a memory, a microcontroller, whatever it is. What is the boundary? Step 3 is then you've identified the product for which you're doing FMEDA, identify all the elements of the product. And for each element, identify their failure modes and failure mode distribution. Step 4 is to estimate the failure rate. Now, this is a very, very crucial step of the process. The estimation of the failure rates can be done either based on real-life data, or it can be done through calculations based on certain standards. Now, estimating failure rates through real-life data involves accumulating a lot of data, which may not be available. Imagine you're making a product for the first time, in which case you'll have to resort to calculations, and there's a lot of mathematics around it, which we'll cover in a separate topic. Once we identified failure modes and the distributions, then we talk about we go to diagnostic analysis and we need to determine if a certain failure mode can lead to a hazard. If it doesn't lead to a hazard, good. If it leads to a hazard, then that's a problem. Then we need to determine what diagnostics exist that can detect, prevent the failure mode. And then we need to decide how good is a diagnostic. Can it detect 90%, 95%, 99%, 100%? How good is it? Then comes step 6, which is to determine the hardware architecture metrics. This is to try to quantify how good the diagnostics are. ISO 26262 recommends these 3 diagnostics. There is the PMHF, also known as probabilistic metric for hardware failure. It is a measure of if a component fails that can lead to a safety goal violation, what is the probability that this component can fail? We want this probability to be as low as possible, which means it's very unlikely it's going to fail. Then there is SPFM, which is a single point failure metric. The single point failure metric is if a component fails, what is the probability that it fails in a safe way? Then there is a latent failure metric, which is if my safety mechanism has a failure, what is the probability that it can be detected? Or if the safety mechanism has a failure, what is the probability that it can be detected by a monitor of the monitor? Now, once we determine these metrics, we then need to decide whether the components and the diagnostics we are using are good enough or not. If they are good enough, all good. If they don't hit the certain metrics that we want for PMHF, SPFM, and FM, then we got to do something about it. Change the components, improve the diagnostics, or a combination of both. And then you have the final step, which is to perform a verification, establish traceability, traceability between components, failure modes, PMHF, SPFM, and LFM. Now, this in short is the entire process. Step 3 to step 7, which involves a bulk of the process, can take a lot of time. And performing a good FMEDA can take several months to perform. We can take a look at as an example of an FMEDA, how to perform an FMEDA, and what the FMEDA is going to look like. We're going to do this with the help of an example which is already explained in ISO 26262.